So we have these things called vectors, like this guy here. What we want to do first is get an idea of what makes a vector a vector. What we'll do in this video is explore the operations we can do with vectors, the sort of things that we can do with them that define what they are and the sort of spaces they can apply to. So a vector we can think of as an object that moves us about space, like this guy here. This could be a physical space or a space of data. At school, you probably thought of a vector as something that moved you around a physical space. But in computer and data science, we generalize that idea to think of a vector as maybe just a list of attributes of an object. So we might think of a house, say. So here's a house. This might have a number of attributes. We could say it was 120 square meters in floor area. It might have 2 bedrooms, say. It might have 1 bathroom. That would be sort of sensible. And it might be worth 150,000 euros, say. And I could write that down as the vector 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. And this, that is, while in physics we think of this as being a thing that moves us about space, in data science we'd think of this vector as being a thing that describes the object of a house. So we've generalized the idea of moving about space to include the description of the attributes of an object. Now, a vector is just something that obeys 2 rules. Firstly, addition, and secondly, multiplication by a scalar number. We'll do this first, thinking of a vector as just a geometric object starting at the origin. So something like this. So we'll get a vector R there. Vector addition is then when we just take another vector. So let's take another vector like this guy here. Let's call him S. And where we put S on the end of R. So then that's S, and therefore if we put S on the end of R, we get a sum that's R then going along S. We'll call that guy R plus S. Now, we could do this the other way around. We could do S and then R, and that would be S plus R. So we go along S and along that way. And that would be S plus R there, S plus R. And we see that they actually give us the same thing, the same answer. So R plus S is equal to S plus R. So it doesn't matter which way round we do the addition. So the other thing we want to be able to do is scalar multiplication, that is to scale vectors by a number. So a number A, say, making it twice as long or half as long, something like that. So we'd say that, say, 3R was doing R 3 times, so that would be 3R there, where A was 3. Or we could do a half R, which would be something like that. The only tricky bit is what we mean by a minus number, and by minus R, we'd mean going back the other way by a whole R. So we take R, we go back the other way, the same distance there. That would be minus R. So in this framework, minus means go back the other way. At this point, it's convenient to define a coordinate system. So let's define space by 2 vectors. Let's call the first one that takes us left, right, and is of unit length, length 1. Let's call that a vector I. We'll have another vector here that goes up, down, a vector j that's also of unit length of length 1. And then we'd say, just use our vector addition rules. If we wanted a vector r here, something like this, that was 3 2's, by which we mean we go 3 i's, 1 I, 2 I, 3 i's, and then 2 j's. So we go 3 i's plus 2 j's, and that gives us a vector r here, just from our vector sum. And what we mean in the 3 2 is do 3 i's added together, or a scalar multiple of 3 i's, and then do a scalar multiple of 3 j's as a vector sum. And that's what we mean by a coordinate system and defining R as being 3 2. So then if I have another vector S, let's say S is equal to minus 1 i's and 2 j's. That is, it takes us back 1 I and up 2 j's, so that's S. Then R plus S would be that. We just put S on the end of R. And then R plus S is going to be, therefore, that total vector. That's going to be R plus S. And we can just add up the components, right? So R is 3 i's and S takes us back 1. So it's 3 plus minus 1 gives us 2 i's. And in the j's, r takes us up 2 and s takes us up another 2. So that's a total of 4 j's. So we can just add up the components when we're doing vector addition. So we can see that because we're doing this component by component, then vector addition must be what's called associative. Formally, what this means is that if we have 3 vectors, r, s, and another one, t, it doesn't matter whether we add r plus s and then add t, or whether we add r to s plus t. It doesn't matter where we put the bracket. We can do this addition and then that one, or we can do this addition and then that one. So a consequence of it not mattering what order we had, so s plus r is equal to r plus s, we can also see that therefore it doesn't matter what order we do the additions in if we've got 3, and that's called associativity. That's associative. That's formally that definition. And vector addition, we can see when we're adding it up like this, will be associative. So I've just got rid of the s's and so on, so we can talk about another issue, which is in a coordinate system, what do we mean by multiplication by a scalar? So if we want to take a multiplication by a scalar, say 2, then we define this to mean that 2r would be equal to 2 times the components of r. So 2 times 3 for i's and 2 times 2 for the j's. Because we've got 2 there, multiplied by 2, and that will give us 6, 4. So 2r would be doing r and then doing another r, so that would be 2r, which would be the vector 6, 4. Go along 3 i's, 4, 5, 6 i's, and up 4 j's. Now, you need to think about another question, which is minus r. So r is this, minus r is then that, which will be minus 3 minus 2. That will be minus r. So then we see sort of obviously, kind of, that r plus minus r is equal to 3 plus minus 3 on the i's and 2 plus minus 2 on the j's, which is equal to 0, 0. So if we do r and then add minus r, we end up back at the origin, duh. Therefore we've defined what we mean by vector subtraction here. Vector subtraction is just addition of minus 1 times whatever I'm doing, putting after the minus sign. So if we think of another vector s, we had s was minus 1, 2 before, right? Minus 1i plus 2j's. So then r minus s would be this. So that's minus s there is equal to go along 1 on the i's and minus 2 on the j's. So r minus s, add up the components, r minus s, let's switch to an addition. So r minus s is this vector here, that's r minus s. If we add up the components of that, it's 3i's plus 1, 3 plus 1 on the i's, and 2 plus minus 2 on the j's. So that gives us the vector 4, 0. So if we do r is go along 3, and minus s is go along 1, we've got a total of 4. And if r is go up 2, and minus s is go down 2, we've ended up going up, down 0 in total. So then we've not only done addition by components, we've done now what we mean by vector subtraction as well, as being addition of a negative 1 multiple of the thing that we're doing the minus by. And that's vector subtraction and addition by components. So let's come back to the house example for a moment. So we said we had a house, that's my house, that was 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. So if I put the units in, that's square meters, that's its number of beds, that's its number of baths, and that's its thousands of euros that it's worth. So 2 houses now is equal to the vector addition of those things is equal to 2, and the way we're defining vector addition, times 120 to 150, which would be equal to 240 4 to 300. So we'd say that in this scheme, the way we're defining it, then 2 houses would be 240 square metres, that makes sense. 4 bedrooms, 2 bathrooms, and worth 300,000 euros if I bought 2 houses identically next to each other. And that would be a scalar multiple or an addition of one house to another. Yeah, one house plus one house. And we could keep on doing that with 3 houses or differently shaped houses or whatever it was, or negative houses. The way we've defined vectors, that will still apply to these objects of houses. So that's vectors. We've defined 2 fundamental operations that vectors satisfy. That is addition, so like r plus s here, and multiplication by a scalar, so like 2r here and minus s here. And we've explored the properties that those imply, like associativity of addition and subtraction, what subtraction really means of vectors, r plus minus s being r minus s. And we've noticed that it can be useful to define a coordinate system in which to do our addition and scaling, so like R3, 2 here, using these fundamental basis vectors, these things that define the space, I and j, which we call the basis vectors or the things that define the coordinate system. We've also seen that although perhaps it's easiest to think of vector operations geometrically, we don't have to do it in a real space. We can do it with vectors that are data science lists of different types of things, like the attributes of a house. So that's vectors. That's all the fundamental operations.